Okay. All the results, all the analysis results are in terms of local axis system. You know, there is a global axis system. Global axes are X, Y, and Z. You can see on the screen right at the bottom there are three axes, X, Y, and Z. They are global axes. Global axes are the axes which never change their orientation. X and Y are always in the plan, and Z is always vertical. Okay? Remember this thing. That's why we call them global. Local axes are the axes which may change their orientation. Okay. What are the local axes? There are three local axes. One, two, and three. Okay. Three local axes. This screen, I'm not sure why the colors are not very good. But each axis 1, 2 and 3 has its own color. If you go to set building view options, click on this, and right here you can display local axis for lines. Line local axis mean local axis for beams and columns, and you can also switch on area local axis. Right now I will do it for lines. Okay, when I do it for lines, then every line you will see has a set of three axes, X, Y, and Z. Oh, sorry, 1, 2 and 3. For example, look at the column 1, 2. The third one you can't see, it's merged here. For example, this means 1, 2, and 3. Okay? Yes. Don't worry about the origin. Origin is not important. Direction is important. Okay? And you can differentiate the colors, but on your screen you may be able to see that these three axes are white, blue, and red. Let me switch off the slabs. Yeah, you are right. Maybe I have to fix the wire. Support the wire a little bit. Is that better? Okay, no problem. I just switched off my slabs. On your screen, you can see there are three axes for every member. Let's talk about beams only, and I am switching off the columns. Okay, and let's focus on one of the beams right here. This is one beam randomly picked. You see three axes. You can't see three axes actually. I can see three axes on the screen. There is one axis here which you can't see. It should be on your computers, right? 1, 2, and 3. Okay. This one is white. This one is blue, light blue, sky blue, and this one is red. Okay. One is red. Okay. 2 is white. And 3 is blue. Okay. Do you see it on your screens? Okay, I just looked at in the new version. The new version has a different color scheme. I think in the new one, you have red, blue, and green. Right? Which version is that? 15. In ETABS 15, you have red, blue, and green. So in your version, axis axis 2 is green instead of white. New version. It is green. Okay. In old version it is white, and in new version it is green. Now, let's talk about beams. This is a beam. Okay. In case of a beam, or in case of a line element, either it is a beam or it is a column, one will always be longitudinal axis. Okay. For line element, one is always longitudinal. Okay. For line elements, beams and columns, one is always longitudinal axis. Which means, which force will be along axis 1? Axial force will always be along axis number 1. In case of beam, right now I am talking about beams, although this statement is generic, but in case of beams, vertical axis is 2. In beams, 2 is vertical. Okay, that's why you will see either white as vertical or green as vertical. Everybody confirms that?
Yes, white.
Okay. It means that which force is along axis 2? Sorry? Shear. Because most of the time our loads are gravity loads. Okay, that's why the vertical shear is along axis 2, right? Axis 3 is out of the plane axis. In beams, 3 is out of the plane axis. Do you understand what does this mean? Out of the plane axis. Out of the plane axis means, look, this is plane of the board, or this is plane where you have seam, or look at this beam. The vertical plane is actually the plane of the beam. When I say out of the plane, I mean to say perpendicular to this vertical plane, which means that horizontal but out of the plane. Axis 1 is also horizontal, but it is longitudinal. Axis 3 is also horizontal, but it is out of the plane. Okay. Which force is about out of the plane axis? It's bending moment. Okay. The bending moment which you have always been talking about is actually about out of the plane axis. Okay. If the beam sags or it hogs, anybody has a steel ruler 12 inches? Scale. Check the scale. Let me see if I have better one. This one is a little short. You have bigger one? No? Yeah. Okay, look at this. If this beam, first of all, let's try to understand the axis. This is 1, this is 2, and this is 3. It doesn't make any difference you say it that way or it is my way, no problem. Okay, when you bend this beam like this, or when gravity load bend this beam like this bending is about this axis, and this is out of the plane axis. So remember that the bending moment due to the gravity load is always about out of the plane axis. Okay, this is for beams. Either it is like this, sagging, or it is like this, which is hogging. All the time it is about out of the plane axis. Okay. So we shall read shear along axis 2 and moment about axis 3, along and about. Right? Everybody clear about this 3? Yes. 1, 2 and 3. 1 is longitudinal, 2 is vertical, and 3 is out of the plane. And remember that 1, 2 and 3 follow the right hand rule. 1, 2 and 3 follow right hand rule. Right hand rule. Which means that if you curl your finger from 1 to 2, then thumb is 3. Okay? Curl your finger 1 to 2. Okay. Curl your finger from 1 to 2 and thumb is 3. Then if you curl your finger from 2 to 3, then thumb is 1. And if you curl your finger from 3 to 1, then thumb is 2. Okay? Thumb is 2. So, one is universal truth, that is, one is always longitudinal axis. That's not going to change whether it is a beam or it is a column. So if I tell you the direction of two of them, then you can find the direction of the third one. Any two you know, and the third one is very easy to find. So everybody is clear about this axis system for the beams. Now let's talk about columns. Okay. As I said before, for 9 elements, one is always vertical. So no question about one. This is one. Now, actually, if you look at it in real life, this is one. 2 and 3 are perpendicular to 1. These are orthogonal axes. So either that is going to be 2 or this is going to be 2. Right? It can be 2 or 2, or it can be 3 in this direction and 2 in this direction. I mean, it can be either way. Okay. Can you go to your screen back and see which one is 2 and which one is 3? Is there any pattern? Look at there. If there is pattern, I'm switching on my columns and I'm switching off my beams, and then I will pick any of the columns randomly. Okay, what I see on my screen, this one, this is a column, this one red, and my case this is white and this is blue. Okay, first of all, see whether this 1, 2 and 3 follow the right hand rule. 1 is vertical, okay, in this case, and 2 is what? 2 is white. This is 2. Okay, 1, 2 and 3. So if you curl your finger from 1 to 2, 3 is that way, right? 1, 2 and 3. You know, in case of column, you can only be sure about axis number 1, that it is always vertical. Okay, but you are not sure about axis 2 and 3, and both axis 2 and 3 may be important for you, because look, in case of column, the earthquake forces may come from any direction. It's not necessary that earthquake would come only this way or only this way. It can be in any of the direction. It can be on 360 angle anywhere. It can be inclined. So the forces in the columns may have component along axis 2 as well as along axis 3. Okay, I mean to say shear forces and bending moment, which is opposite or which is different from the beams. In case of beams, generally the loading is gravity, and earthquakes affect columns much more than beams. So in case of beams, our shear force mostly is about axis number 2. If you see shear 3, horizontal shear, that will either be absent or it may be absolute minimum. So in case of beams, only axis 2 is important for shear and axis 3 is important for bending. But in case of columns, shear can have components in both the directions, 2 and 3. Movement can be about both the axes, axis 2 and axis 3. Even if you neglect earthquake, for example, look at a corner column. Corner column has biaxial bending. Okay. Now biaxial bending means movement about axis 2 as well as movement about axis 3. Okay. So both axes become relevant to shear force as well as bending moment. Okay. So you don't have to memorize the directions of local axis, especially for the case of columns, because you have to see forces for both of them. But you need to understand from the colors that which is axis 2 and which is axis 3, so that you can provide the reinforcement in the at the appropriate place. Yes. We design it for shear as well. Look, in case of beam, the major shear is along axis 2. It's vertical. Why? Because load is gravity. You have no horizontal load. Okay. Yes, there can be horizontal load due to earthquake, but the major effect of earthquake is on the columns and minor effect is on the beam. So you won't have significant horizontal shear. Horizontal shear means shear along axis 2. So major shear is about axis along axis 2. Now bending moment. Bending moment, again, because you have gravity loads on the beams mostly, so bending moment is either like this in the midspan or it's like this on the support. Both of them are about which axis? It is about axis 3. Okay. So gravity loads are producing bending moment about axis number 3, and beams mostly have gravity loads. That's why M3 is important. Okay. Do you have bending moment in the beams like this? Very, very small magnitude, maybe because in case you have horizontal load somewhere. This bending moment or this bending moment. Okay. This bending moment is about which axis? It's about axis 2. So that's why I'm saying that movement about axis 2 is insignificant in case of beams. That may be significant if you have horizontal loads, which may be present but not of significant magnitude. It may be due to earthquake, it may be due to wind forces, because both of them are horizontal forces. Yes. Look, 2 and 3 are different axes. 2 and 3 are not same axes. Yes, that's what I said, that in case of columns, you can have movement about axis 2 as well as about axis 3, even in gravity loads. And I said about corner column, that in case of corner column, you have biaxial bending. You have movement about both the axes. For example, look at column on the side. This is a column on the side. Okay. Or let's talk about this column. This column has an equal area to take care on right side as well as on the left side. So load is kind of balanced. So you won't see significant bending movement in this direction. In this direction means about this axis. So this column won't have significant bending moment about this axis. But how about this axis? Look, this column has like 15 feet tributary area on one side, but on the other side, outside, there is no load. So all the load is on this side, which is actually, when you calculate the resultant, that would lie somewhere here. So that is an eccentricity, and this column may have movement, or definitely it will have movement about this axis. So this column has movement about this axis, but no significant movement about this axis. It means this is a uniaxial column. Okay. Although this is not perfect example, this is a masonry column. Masonry columns do not have bending moment because that support is either a hinge or a roller. I am talking about a frame, a concrete frame. So remember this thing, that corner columns have biaxial bending. Okay. Edge columns mostly have uniaxial bending. They may have biaxial bending if there is unsymmetrical loading, okay, but not significant. And a column in the center which has stability area on all four sides approximately equal, that will mostly have significant axial force but no significant bending moment. And if it is perfectly symmetrical, then theoretically there shouldn't be any bending moment, right? But practically you may have some bending moment because all the time you don't have. I'm sorry for this. Okay. So corner columns biaxial bending, edge columns uniaxial bending, and perfectly centered column have axial force and no significant bending. Now these are general statements. There may be some variations, right? For example, let me give you an example of variation. I said that this column is an edge column. It has uniaxial bending because this way they are balancing. This side is balancing this side. If you calculate the resultant, that will lie on this line somewhere. If it is in this line, then eccentricity is practically zero. Okay. There may be a situation where on this side of the beam you have different loading. Maybe there is a store and heavily loaded, and on this side you may have an office. Load is less. So when there is an unloading, although the dimensions are symmetrical, but the magnitude of loading is unsymmetrical, then you will have bending moment about this axis as well, right? Oh, sorry, this axis, this bending moment. Okay. So the point I want to make is that you cannot make a universal statement that edge column is always a uniaxial column. Generally it is, but when there is an unsymmetrical loading or unsymmetrical dimensions, then edge column may also have biaxial bending. Okay. But in this case, for example, this column, if this is of concrete, then it won't have. It will be a uniaxial column. I don't see much of a difference on either side. Okay. So in case of columns, one is vertical or one is longitudinal, and the 2 and 3 can have any direction, satisfy the right hand rule. Okay. For example, in this case, it is like this and like this. All of them are at right angle. Okay. This is 2 and this is 3. So 1 is longitudinal. One is longitudinal. And 2 and 3 are have such a direction that right hand rule is satisfied. Okay. Yeah. So you have to look at it and see where you have the direction of axis. Let me do an experiment, small experiment on this. You can see two columns. If I delete this column, I'm deleting this column and I am installing the column again. What was the size of our column?
18.
All of them? Okay, I was just trying to see if I draw it from top to bottom or bottom to top, it makes any difference. It doesn't make any difference. You draw it from top to bottom or bottom to top, the axis doesn't change. So right in this model, all the columns have same direction of the local axis. This is, you see in plan, you don't see axis number 1 because it is longitudinal axis, it's inside the screen. You see only axis number 2 and axis number 3, and on my screen this axis, these horizontal axis are axis number 2 and the vertical axis are axis number 3. This is plan of the building. Okay? Everybody clear about this? Okay, so this knowledge is very, very important for you to understand the results. If you don't have the knowledge of local axis system, you can never ever understand the analysis result. Okay. Then let's talk about area element. This is beam and column. Let's talk about slabs. Slabs / walls, or you can say area elements. Okay. This is a slab. Okay. So, in case of an area element, a universal truth is that axis 1 and axis 2 are always in plane axis. Axis 1 and 2 are always in plane. In plane. In plane. It's not plan. It is plane. Look, this is plane. Axis 1 and 2 always be in plane. Means either axis 1 is like this and 2 is like this, or 2 is like this and 1 is like this. No matter this area is horizontal, or this area is inclined, or this area is vertical like a wall. If this is vertical like a wall, then axis 1 and 2 will be, maybe axis 1 is like this and 2 is like this, or 2 is like this and 1 is the other way. We'll figure out, but always remember this in mind. 1 and 2 will always be in plane. So if 1 and 2 are in plane, the third is out of the plane. Okay? It's a slab. Then 3 is vertical. Okay? Out of the plane is vertical. If it is a wall, then 3 is horizontal. Okay? Clear? So instead of saying horizontal and vertical, we say in plane and out of the plane. This is generic, and it is true for the slabs as well as for walls. Okay. Axis 1 and 2 are always in plane. Axis 3 is out of the plane. Okay. Now let's try to see this in our real structure. Okay, I will switch on my slabs or floors, and I will, from here, look, I will switch off my line local axis and switch on my area local axis. Press OK and see a 3D view. and I also switch off my columns, they are disturbing my view. I can also switch off my grid lines and see only and only my slabs. Okay, now let's focus on any one of them. For example, let's do this one. Okay, so you see that this is red, this is white, and this is blue. Okay, one is red and two is white, or some of you may have green, and three is blue. So 1 and 2 are in the plane of the slab, and 3 is out of the plane, which in this case is vertical. Okay. Now, a slab, for example, it's a two-way slab. Two-way slab bends like a bowl, which means it has bending moment in both the directions. Okay, it will have movement about axis 1 as well as about axis 2. So in case of slab, it will have movement either about axis 1 or 2, or it may have movement about both the axis 1 and 2. It depends whether it is behaving one way or it is behaving two way. Okay. But in case of finite element analysis, you will see that it may always give some contribution to the other direction, even if it is one. When we say one way, perfectly one way slab, a 4x supported slab is not 100% one way, although the dimensions say that it is one way. Yes, a 2x supported slab is perfectly a one way slab. But if it is 4x supported, although, for example, this panel, look at this panel, it is 4x supported, but if you get the B over L ratio, then that will tell you that this panel is one way, which means that it should bend like this. Okay, that's your span. But it doesn't mean that it will not bend in that direction. It will, part of it. Okay. In theoretical in manual calculations we ignore that, but when you do finite element analysis, you will have some bending moment in the other direction as well. So the bottom line is that in case of slabs, the bending moments are about in plane axis, either 1 or 2 or both of them at the same time. When you have a two-way behavior, then of course about both of them. And shear is about which axis? It's about vertical. It's along vertical axis because we have mostly gravity, right? Have we described all this? So in case of slab, we shall talk about M1 and M2. But in case of and shear 3. Okay. Now you see, in case of beam, shear is in along which axis? But in case of slabs, shear is along axis 3. Okay. So you need to understand the differences. Many students, they don't understand this local axis system. So when it comes to results, they are always confused about the results, and sometimes they make mistake because they consider the force in one direction mistakenly to be in the other direction. These directions are important because you have to provide reinforcement accordingly, right? For example, if you are confused in these bending moments M1 and M2, and by mistake you take them opposite, then what is the end result? End result is that maybe you provide more reinforcement in that direction and less reinforcement in this direction. So it will be opposite, right? So if it is opposite, then definitely your slab is not going to survive, or it will have cracking. So be very careful in reading these movements, because these movements are ultimately translated into reinforcement. Okay, so make sure you understand this local axis system. Vertical is 3, this is 1, and this is 2. But remember that this 1 and 2 may be interchangeable. So you have to look at the slab and display the axis and then see which one is 1 and which one is 2. Both of them are in plane. They may be switched in some cases, it depends. I'm not sure about this. So, but you have basic understanding that 1 and 2 are in plane, and again they follow the right hand rule. Okay, they always follow right hand rule. Okay, did we apply loading on our structure in our last class? Okay, we can check just by right click and see the loads. We have floor finishes of 50, live load or partition load of 70, and live load of 100. Okay, now before we do the analysis, we have to do meshing. Without doing meshing, your analysis is not correct, or I should say, if you don't do meshing, your analysis is completely wrong. Okay, what is meshing, or what is a mesh? Mesh is this. This is called a chicken mesh. What do you see? You see chicken? Okay. But I see a mesh. Mesh is something which has either these orthogonal boxes or maybe other shape which is repeated, and it creates a pattern, right? You don't see a mesh here. Right now, our slab is like a surface, okay, like this. We have to convert this from this to this. Why? Okay, you are studying structural analysis or structural engineering, and there you may be studying stiffness method. Okay, when you solve a structure by stiffness method, or an advanced analysis which is finite element method, then you divide your structure or structural element into small portions. If you have done analysis of a beam, then you may have chosen some nodes. One, you have supports, and in between you can choose several nodes, right? On every node, at the end of analysis, you will get shear force, bending moment, and displacements, right? So, when you convert a solid surface into a mesh, you are actually creating nodes, okay? And in the end, you will get the forces and displacement at every node, okay? But this is not the only objective. Okay. Maybe let's do it wrong, and then we learn that if we do it wrong, what's the problem? And then we correct it and see how it goes. Right now, I have not done meshing. My slabs are like solid surface, okay? No nodes in between. So we'll see what happens. Okay. I will go to analysis. let me save it first. I will go to analyze, and in analyze you will see some options here. For example, set analysis option, for example check model, and then run analysis. Let's do set analysis option. The first thing out of these three or these four, you have to pick. If it is a three-dimensional structure, which our structure is, you pick this one, full 3D. Okay, it's not a plane structure, not a plane frame, it's a 3D structure. And then you have these options: dynamic analysis. Dynamic analysis is generally done for dynamic loading, which is earthquake and wind. So in our case, we will uncheck dynamic analysis. Okay. The other is include P delta. What is P delta? I'm not sure if we have studied B column. Did you study anything about moment magnification in concrete when you were studying design of columns? Yes, sir. Moment magnification is magnification in the moment due to eccentricity. Okay, that eccentricity can be produced due to two reasons. One reason is that you have some lateral loading, and due to lateral loading your column is not vertical but it has moved and it has a sway. This sway is called what? Delta. So this delta creates eccentricity. So the load which is applied, the gravity load, that gravity load into this eccentricity produces a secondary movement. So this additional movement is called P delta effect, which is in addition to your regular or traditional bending movement. Okay, this is generally where when you have either lateral loading or you have bending movement on your column, which is generally the case all the time. For example, if this column has only axial force, no eccentricity, okay, then you can design it as an axial column. But if this column has bending movement as well, it will bend like this. So load is here and the column has bent due to bending movement. Then the column has eccentricity right here from with respect to the vertical line. The vertical line is here, but when the column has bent, an eccentricity is created right here in the middle. This eccentricity. So that load into this eccentricity at the center, that creates an additional bending movement. So that additional bending movement, to take care of that additional bending movement, you have to magnify your bending moment and do the moment magnification. So that is here, include P delta effect. So that is more realistic in short sense, or in the shortest way of saying it, that P delta analysis is more close to reality, or in other words I should say that magnifying the movement is more close to reality as opposed to not magnifying movements due to eccentricity produced by lateral loads or by the bend movement. So as a beginner, because you have not studied P delta analysis, you can start with without including P delta analysis. If you check it, then you may have to set some parameters which we can learn later on, but as a beginner you can uncheck this option. But on your notes you can write this thing so that we won't forget in the future. You say write this option, analysis option, include P delta analysis, and in the bracket you can write to be covered in future. Okay, and highlight it so that we may remember it. I think there is another thing before. What was that? Earthquake.
Load combination type.
Load combination type. Mass. Yes, iterative. That was special seismic effect and the masking. Okay. So as a beginner, I am unchecking this option. So on this panel, we have just make sure that we are doing full 3D analysis by clicking this option. Press OK. Second thing on analyze is check model. Check model means checking the model for any error in connectivity. Okay, connectivity means where you have connected the beams and columns, were those connections correct or not? Okay. Look at this. Check, when you hit check model, it has several things. For example, it says line checks, point checks, area checks. Okay, in line check it says line overlap, line intersection within tolerance, line intersection with the area edges. Okay, let me run this and see if we have any error. Okay, no warning. The model has been checked and no warning messages. Fine. Let's do something wrong. Okay. Just go somewhere. Pick the reshaper. Hit the reshaper. And do this. No, it's not agreeing. Okay, let's try something different. Okay, now it works. Maybe it doesn't work in 3D, I'm not sure. Yeah, you have to try. So what we did, we have picked a beam and disconnected from the column. Now this beam is hanging in the air. It is not connected. Okay. Okay. Now we go back to analyze and check model, and yeah, actually, you know, last time we missed these checks, but still there was no error, I think. Yeah, that's what we have to learn. It doesn't show any warning. Why? Tolerance. You missed one thing. Okay, right here it says 0.1 inch. Let's make it okay. Check model. Okay, let me change this to say 10 inches. Okay. What happened? Now read these warnings. Model has been checked. 4 warning messages. Story 1, B42 and B2 are too close. Now we would ask that what beam is B42 and what beam is B2? How can we get that information? From the line labels. Okay. So I will copy this and I will go to Notepad and paste it here, because once I close this I can't get it back. So I want to know that what is that B42 line label. Okay, now I have it. Okay, this beam is B42, this beam is B2, this beam is B1, and this area, let me switch on area levels as well. This area is F2. So warning number 1 is okay, warning number 1 is that B42 and B2 are too close. They are too close. Okay, remember this warning. This is B42 and this is B2. So warning is that they are very close. What software is thinking that you have mistakenly disconnected them, or when you were clicking there at the time of modeling, instead of hitting at the right spot, you mistakenly hit somewhere else. Okay, that's what the understanding of software is. I go back and check model and change my tolerance to 7 inches, and let's see what I have. Now you don't have a warning. Okay. This is our joint. Okay. This is B2 and right here is B42. Right? When my tolerance was 10 inches, the software provided me a warning. Okay? When my tolerance was 7 inches, the software did not provide me warning. Okay? What's the difference? Whatever warning, whatever tolerance you will provide, for example, if I provide 7 inches, if two of my members are within 7 inches and not connected to each other, then software will think that I have mistakenly disconnected them or not connected them. Okay, let me repeat myself. If I give 7 inches tolerance and two of my member ends are within 7 inches distance, then software will think that I have made some mistake while clicking on the right spot and they are mistakenly disconnected from each other, and it will turn up a warning. Okay. Now for 7 inches tolerance, if my two members are more than 7 inches away from each other, then software will assume that I have purposefully disconnected them. It's not a mistake, but it's my purpose that I have to model it that way, and it won't turn up a warning. So right now, my two members, B42 and B2, are more than 7 inches away from each other, but they are less than 10 inches away from each other. So when I make my tolerance 10 inches, it turns up a warning because the distance is less than 10. When I make my tolerance 7 inches, then there is no warning, and software assumes that I have done it by purpose, by intention. Okay? You understand that? Yes. Okay, very nice. Generally, when I have been designing real life structures, there is no universal value of the tolerance. Look, because it depends on your mistake. Ideally, what do we want? We want that all our beams and columns should be properly connected. We can't say that, okay, they are 0.1 inches away and that is acceptable to us. No, that's not acceptable to us. For us, the tolerance is, for us, it has to be properly connected. But you can keep it 0.1 inches, maybe. You can try 0 inches. I'm not sure that's what you can do by yourself. But you should understand the concept that if two disconnected members are within the tolerable distance, then software will issue a warning. If they are beyond that, then it won't issue a warning. Okay? Now, our first warning was that B42 and B2 are too close, and I think that this is the distance, 8.745 inches. So you see, it's more than 10 inches or more than 7 inches, but it is less than 10 inches. Similarly, it says F2 and B42 are too close. It's talking about this slab and B42. So B42 is close to beam B2 as well as it is close to the area F2. So it is getting warning for both of them. And then it says story 1, 27 and B2 are too close. Now what is 27? It's a point. Okay. If I switch on point labels, then this my beam B42, this edge, that point on the edge is point number 27. Okay, so point 27 is also close to the beam B2, and point 27 is also close to F2. Okay, so the software is issuing warning for the line element, area element, and for the point element, all of them. So for one mistake, you are getting 4 warnings. If you correct that mistake, then there won't be any warning. Okay, so you have to check your model all the time before analysis, so that you make sure there is no connectivity problem. This is connectivity problem. Sometimes there is an overlapping problem. Okay, I will fix this by reshaper. Pick it up from here and place it back, and now it is fixed. Sometimes you have for example, this area, if I pick this area and do it like this, okay, so you see that this area and this area, they are overlapping. Okay, and if I let's make a small, this is too big, let's make a small change. So instead of here, I just do it like this. So you see, it's a very small. Okay, very small. Can we make a better look? No, it's not better. It's worse. No, it's worse. No. Let's go back. Sections. Okay. So if you go to check model, and let me make it this difference maybe 2 inches. Okay, say if my tolerance is 3 inches, then it gives me warning. It says that it's 0.9998 inches, so it's 1 inch. F18 and B10, the beam, they are too close. This warning is about the point. This warning is again about a point and a beam. And look at this. F1 and F18 are too close. F1 and F18. One of the area is F1 and the other area is F18. They are too close to each other. So that will turn up a warning. So you have to make sure that all the lines and areas are properly connected. Now we shall go to the analysis and try to understand the results. Yes. We'll do it without meshing, and then I will show you that if you do it without meshing, what's the problem? That we can have a break in the class. In the class. You can sit here and you can relax. And it's very hard to bring you back to the class, so I don't want to waste my time. From next time we may have 5 minutes break in the middle at around 2 p.m. But not today. Okay, the break is over. We shall do the analysis now, and I'll go to analysis tab and I will run analysis. Running analysis is very quick. Okay. In case of new model or new version, you may, when you hit run analysis, you may see a panel where it asks you to switch on, it says run or do not run. Run or do not run for specific load case. For example, we define live load and dead load, partition, floor finishes, and the other one roof details. So in new version, you can switch on or off analysis for a specific load case. In old version, it doesn't ask you for switching on or off analysis for a particular load and runs analysis for everything. Okay. So in the new version, you may have a different panel which you can use to pick for what load you want to analyze and for what load you don't want to analyze. What you see on the screen right now is deformed shape of your structure, and for what load this deformed shape is, that is right there in the title bar. Do you read that? This deformed shape is called floor finishes load. And by using these arrows, you can switch to deformed shape of other loads. When I hit this, you will see that floor finishes FF will change. Now it is for roof. There was no roof load, that's why you don't see any deformation. This is for partition load, right? And now this is for live load. This is, remember, this is exaggerated deformed shape. Okay? And right from this button, show deformed shape, or from display, show deformed shape, you can actually pick for which load or for which load combination you want to display the deformed shape. For example, I want to do it for live load, and you can choose a scale factor. For example, if I say, okay, magnify it to 10,000 times, okay, magnify it to 10,000 times, then real. Wow. Okay, that's a little bit too much. So I make it say 1,000 times. That's better, right? So you can scale it up, scale it down. You can also see the animated shape. Okay. Now, there is a problem with this deformed shape. What's the problem? With the deformed shape, not with you. Nothing wrong? And there is something wrong with you. There is something wrong. Yes, that is right. Okay, listen everybody. So what is the problem in this deformed shape? Yes, the deformed shape tells us that beams are moving independent of slabs. Right? They are disconnected completely. That's the problem. That tells us that our analysis is wrong. In reality, you see that the slab is continuously connected with the beam, right? But in this case, the beam is only connected at the edges to the columns. So what is happening is that slabs are not transferring the loads to the beams, but slabs are transferring the load to the columns because slabs are connected only to the columns. So, in this case, okay, if you come here or maybe here, display, show deform or show member forces, and if you look at the frame forces, which is actually beam or column, and you see for live load, if you see bending moment, what bending moment? Oh, I rubbed it. For the beam, which bending moment? It's about 300. Yes, sir. So I see M33. Okay, that's okay. And okay, this bending moment. Okay, on this panel you can see the load, the distributed load, and this is shear force diagram. Oh, this is completely black on the screen. Do you see it on your screen?
Yes, sir. Yes, sir.
But at least you can read the values. Actually, there is shear force diagram, there is bending moment diagram, and this is deformed shape, which is not visible on you. But you see these values: 2.72 shear, 8.38 movement. Okay, and right here is the load diagram. And right now we are looking at values at this location. But you can move this anywhere. So along the length of the beam, right here, the shear is this much, movement is this much. At the center, what is the shear in your case? Near the center? Near the center. It's almost zero, right? It's almost zero, 10 is for minus 3. And this is the movement. You have negative movement on the supports, and you will have positive movement right here in the middle. Okay, the point I want to make is about meshing. Okay, we have to discuss the results, but before that we were actually looking at the meshing and the connection. So that's what I want to focus right now. If you want to switch off these bending moments, you can hit this button, show undeformed shape, and it will be back. Okay. So what we saw in the deformed shape was that beams and slabs were not connected to each other, right? That's what we saw. How can we connect them and make them behave like in real life? For that purpose, we need to use the option of meshing. When you do meshing, software will create this meshing, and at every node, the software will connect the slab to the beam. At every node, slab will connect it to. For example, let's assume that this is a beam and this is a slab. So there are maybe more than 50 nodes along the length of the beam. So software will connect this slab to this beam at every single node. Will that be a continuous connection like this? It will not be a continuous connection like this, but it will be close to a continuous connection. Right now, there is no connection. Okay? So, we shall go and do meshing. For that, okay, when you do the analysis, the model is locked. I will unlock the model. Once the model is locked, you can't edit anything. Press OK. I'm going to switch off my labels so that I look it better. And I'm looking at the plan right here. So I select the slabs. Maybe you can't see, but you can read this. So I'm selecting one by one all of them. So my 16 areas are selected. So you select the areas and go to assign and go to shell area and area object mesh options. Shell area, shell/area, area object mesh options. Okay. You have to select the slab, otherwise this option will be dead. First of all, you have to select all the slabs, only then the option will be active. Okay, press OK, click it and you see this panel. Okay, it has two distinct areas. The upper one, this one is related to the floors and this one is related to the walls. So right now we are concerned with this one. Okay, what it says, right now it is default auto mesh at beams and walls if membrane. What was our type of slab? We defined it as a membrane, right? So in case of membrane, it does some auto meshing. Auto meshing means software mesh it by itself. Okay, so maybe by default software has done some kind of meshing. Okay, but we don't know about that. But no auto mesh if shell or plate. If you have defined as the slab as shell or plate, software doesn't do auto meshing. You have to do meshing by yourself. This is one option. You can pick any of these four options. For example, second option is for defining rigid diaphragm and mass only, no stiffness, no vertical load transfer. This is not related to gravity loading, so we skip this. This is more of lateral loading. No auto meshing. Use object as structural element. We won't go with this option. We won't meshing. Okay, this is the best option. Auto mesh object into structural element. The fourth one has more flexibility. So we will do auto meshing, but we will define certain things. Okay, mesh at beam and other meshing lines. If there are lines or beams, mesh it on those lines. Second, mesh at wall and ramp edges, on the wall edges if there are edges. Mesh at visible grids. Wherever those grid lines are there, mesh it at the grid lines. And in our case, our grid lines are passing through the beams. So biggest mesh is actually equal to the whole panel. But the best option is further subdivide auto mesh with maximum element size of this. The element size you plug in. What is the size of our panel? It was 15 feet or 12 feet? Okay. We can see this is 0 and this is 14.9. It's 15 feet panel. Okay. Go to, we have already selected, go to assign, shell area, mesh options, fourth option, further subdivided into maximum element size of this. What is this? This is the dimension in the units here. If my units are feet, then this means 4 feet. So you are dividing it into a mesh of size 4 feet by 4 feet. But our panel is 15 by 15. If I make it say 3 feet, 3 feet means it will divide it into 5 elements. But in total, how many elements in a slab of 15 by 15? If the slab is 15 by 15 and mesh is 3 feet by 3 feet, it means 5 on this side and 5 on this side. So total elements will be 25. There is no recommended size of mesh. If you keep on increasing the mesh size, your accuracy will be better and better because you will be more close to continuous connection. If you have 5 meshes, it means your slab is connected at 6 locations, right? 6 locations. 5 meshes, locations are 6 points it is connected. But in reality, it's continuously connected. So if I make my mesh size 1 feet, then in 15 feet I will have 15 meshes, means 16 connection points, right? So more number of meshes, or I should say smaller mesh size results in a better quality analysis because you become more close to reality. But after a certain mesh size, if you keep on increasing the number of meshes, the results are not changed much. So it's like optimum moisture content, you remember? And that also is burden on your memory. If you have a very small mesh size, for example, if you say, okay, let's have a mesh of 1 inch by 1 inch, then in 15 feet square panel, you have so many meshes, right? So many elements. And then there are so many slab panels, and there may be so many floors. So your time of analysis will increase tremendously. So you want to keep it in a limit, okay? Generally, my experience is that if you have a 2 feet by 2 feet size of panel, size of a mesh, it works fine. But then you also have to see the dimension. For example, it is 15 feet, so let's make it round number. So instead of having 2 feet, you can have 3 feet, or you may have 1.5 feet. So you end up in a round number. Okay. So let's make it 1.5 feet. So your mesh is 1.5 feet, 1.5 feet square. Save it. You won't see the mesh, but you will see something written as MESH, mesh. It's already meshed. Now we do the analysis. This time, analysis will take more time than our previous case. Okay? Why? Because it has more elements to solve. Before it was considering entire slab as one element. Now in one slab, there are so many elements. 15 feet by 15 feet. How many meshes? Yes, 10 on one side and 10 on, it means 100 elements. So in our previous case, there was one element, now it is 100 elements. So that's why it is better to have little bigger mesh size. Maybe 3 feet by 3 feet would have been better. But no problem, we have time. It has all the details about how many elements and how many joints and beams and all that. It maintains the logs which you can see. Okay, now look at it. You see meshes now. Let me see if we can have better color. That's better. Okay. So after it has performed the analysis, then you can see the mesh. Okay. This is, each mesh is 1 feet, 1.5 feet by 1.5 feet, and this is deformed shape under live load. Wow. Something is wrong. No. I just did it one. Okay. That's a signal that we should finish the class. Okay, that's when we didn't have any load, right? I am not sure what happened. Now, what's happening is, it is showing so much deformation. Okay, I did it auto instead of putting the scale by myself, but okay. What do you see now? You see that slabs are behaving like a two-way panel and bending like a cup. And let me see if it now the slabs are connected to the beams. Previously, beams were disconnected from the slab. But because slabs have more deformation, that's why you don't see the beams deforming much. Okay? Relative deflection is more. But after meshing, you can clearly see that slabs, you see, slabs are connected to the beams. Completely connected. So this is more close to the real situation. Oh, it is just for entertainment. It won't go up in real life, it will go down. Okay. You know, looking at the animation is important, because if by mistake you have not connected a member properly, then when you see the animation, it will like fly in the air like this. So you will figure out that, okay, this connection is not right. Okay. I mean, if you had such a tolerance value that software was not able to catch it within that tolerance, then you can catch it here. Anything which is not properly connected. Okay? Okay, we stop yesterday. Yeah, okay. Let's go back. Okay, thank you very much.